the last class we are looking at this 3D space frames, and let me summarize what we have done. We have looked at the element equations, the derivation of element equations, and also in the last class we looked at the transformation matrix from local to global coordinate system, which is required for transforming these element equations which are in the local coordinate system to the global coordinate system. And so let us briefly look at those things once again. These are the element equations which are based on axial force effects, bending effect in xy plane, bending effect in xz plane, and also torsional effect. All these effects put together, and assuming all these effects are uncoupled under small deformation theory assumption, we obtain these element equations. Here these coefficients A1, A2, A3, A4 are defined like this. The previous equation, element equation, can be compactly written as KL dl is equal to RL. So since this is element equations system in local coordinate, in local coordinates for a particular element, so using this equation we can assemble element equations for all elements once we know the material properties and also geometrical properties. And once we have all the element equations in the local coordinates, in their respective local coordinates, we need to convert them into the global coordinate system before we assemble the global equation system for solving the nodal values. So this is the transformation for the displacement vector in the local coordinate system to the displacement vector in the global coordinate system, where R here is the rotation matrix, 3 by 3 rotation matrix, and 0 is also 3 by 3 null vector. So transformation matrix is going to be 12 by 12 matrix, and this rotation matrix comprises of all the direction cosines Lx, Mx, Nx, Ly, My, Ny, Lz, Mz, Nz. So in the last class we have looked at two kinds of methods to calculate these components of direction, these components of this rotation vector, which are the direction cosines. The two methods that we looked in the last class are orientation angle method, and under orientation angle method we looked at a special case in which local y axis lies in the same plane as global xy, and also we derived for a general case of arbitrarily oriented frame element using orientation angle method. But the problem with this orientation angle method is calculation of orientation angle is not easy in many practical situations. So that is why we have the other alternate method, which is third node method. And before once again this orientation angle method, the data that is required is for the case of arbitrarily oriented frame element, the data that is required is angle alpha, which is measured in the counterclockwise direction from global y axis to global x axis, and that is the angle by which the element needs to be rotated about local x axis such that local y axis is parallel to the global y axis. So, we require that in addition to the coordinates of the endpoints of the space frame element. So, this is the data that is required for orientation angle method. And now let us look at briefly that method. This rotation matrix R consists of direction cosines. These are coming from the coordinate transformation from the local x y z to global x y z, consisting of all direction cosines. So, this is R matrix, and this is the formula for obtaining direction cosines using orientation angle method for the case in which local x axis lies in the same plane as global x y, and here you can see Lxy is in the denominator. By definition, Lxy, if you recall, it is square root of Lx square plus mx square. So, in case Lxy is 0, then we will have problem in calculating. So, in that case we need to look at the element, space frame element, and by inspection we can write the rotation matrix components in case Lxy is equal to 0. Lxy is going to be 0 in case the frame element, space frame element is oriented or it is parallel to the global z axis. So, for these cases, the components of rotation matrix can be obtained by inspection. Case A is shown there in the figure. You can easily see by inspection what is cosine of angle between small x axis, capital X axis, small x axis, capital cosine of angle between small x axis and capital Y axis. Similarly, other components, that is cosine of angle between small x axis and capital Z axis. So, Lx, Mx, Nx. Similarly, you can find Ly, My, Ny, Lz, Mz, Nz. So, for the element, space frame element, which is shown in figure A, the element is parallel to global Z axis. In that case, we can easily check the rotation matrix by inspection is going to be whatever is given in the slide. And for figure B, if the element, space frame element is oriented in the manner which is shown in figure B. So, the difference between figure A and figure B is the way the nodes are numbered. In figure A, whatever is numbered as node 1 is 2 in figure B, and whatever is numbered as 2 in figure A is node 1 in figure B. Because of that, the orientation of local x axis, y axis, z axis are different. So, even the rotation matrix is going to be different. So, for case B, rotation matrix again by inspection and just observing what is going to be the cosine of angle between the local axis and global axis, we obtain this one. So, this is using these we can calculate the direction cosines using orientation angle. So, this is what we have seen in the last class, and the last case is general case of arbitrarily oriented frame element. In this case, first thing what we need to do is we need to rotate the given frame element about local x axis such that local y axis is parallel to the global y axis. So, in this case of a arbitrarily oriented frame element, rotation matrix is given by this one. Again, in the special case where Lxy is 0, we get rotation matrix by this one. It can be easily checked that in the limit Lxy tends to 0, the first the components which are there in the first rotation matrix reduces to what is given in the second rotation matrix. In these matrices you have C and S. C is cosine of alpha, S is sine of alpha. Alpha is nothing but angle between the global y axis and local y axis measured in the counterclockwise direction, or the rotation by which we need to rotate about x axis to make the global or local y axis parallel to the global y axis. Cosine of that and sine of that is what is C and S respectively. So, using this rotation matrix formula we can obtain for for any arbitrarily oriented frame element the rotation matrix. So, this is by rotation angle method, and as I mentioned, calculation of rotation angle is not easy in many practical situations. So, the other alternate method is third node method, in which actually third node is, we need to define a third node because this third node is going to be used to define either local xy or xz plane, and whatever we have seen the formula in the last class, it is based on third node being used to define local xz plane. So, schematically it can be explained using this figure. Here a arbitrarily oriented space frame element is shown, in which local x axis is such a way that it is going a vector going from node 1 to node 2, and local z axis, local y axis are also shown. In addition, a third node is also shown in the figure to define xz plane, and once we know the vector 1 2 and 1 3, cross product of vector 1 3 and 1 2 gives us local y axis or vector along local y axis, and when we normalize it we get unit vector along local y axis. And once we know the vector along y axis, and using the nodal coordinates of 1 and 2 nodes, we get local vector along local x axis, and cross product of vector along local x axis times local y axis gives us a vector along z axis, which we can normalize to get unit vector along z axis. Once we have the vectors along unit vectors along local x axis, local y axis and local z axis, we can easily write what is this rotation matrix, because the components of this vector are going to be the components of the rotation matrix. So, this is about third node method. So, what additional information we require is, we require a third node to define either plane xy or xz, but we usually take one of the existing nodes in the model as third node, which will be clearer to you when we solve a problem. So, using this or using these any of these two techniques, that is either rotation angle method or third node method, we can calculate the rotation matrix, and once we get the rotation matrix, the element equations in the local coordinate system can be transformed into the element equations in the global coordinate system. And so, the assembly and solution procedure for nodal degrees of freedom, the procedure is standard procedure which we are following till now. After a model after a nodal solution is obtained, the displacements, axial forces, moments and shear at any point along the 3D frame element can be computed using shape functions and its derivatives, as we are doing for the frame plane frame or trusses or beams that we have seen till now. For each element, global displacements can be transformed into the local displacements, because when we want to calculate these axial forces, moments and shear, whatever, when we solve the global equation system we get global displacements in the global coordinate system. We need to convert back into the displacements in the local coordinate system, because using this we will be calculating axial forces, moments and shears, or even displacement at any point along the frame element. For an element with a uniform load Qy, Qz, Qy in the xy plane, Qz in the xz plane, the equations in terms of local coordinates, that is s is equal to 0 corresponds to node 1, s is equal to 1 corresponds to node 2. In that case we can calculate, once we get the local displacements or displacements in the local coordinate system for that particular element, we can calculate axial force using this formula, and shear Vy, capital V is used to denote shear as a function of s. Again s is equal to 0 corresponds to node 1, s is equal to 1 corresponds to node 2 is given by this. And you can see the second part in this equation, it is a correction term for fixed end solution. Here the correction term that is shown in the slide is corresponding to uniformly distributed load case. If it is some other load case, we need to use the corresponding fixed end solution for shear, and shear Vz is given by this one. Again here we have fixed end solution correction for uniformly distributed load case. So using these formulas we can calculate axial force, components of shear and torsional moment. Here in the formulas we have the nodal values d1 to d12, and these have same meaning as what we have seen in the last class. They comprises of all the 3 translational degrees of freedom at node 1, 3 rotational degrees of freedom at node 1, again 3 translational degrees of freedom at node 2, 3 rotational degrees of freedom at node 2, and moments My is obtained using this formula. Again please note that for axial effects and torsional effects no correction is required, fixed end solution, because we are actually writing formulas for the case of uniformly distributed load. If it is a problem in which temperature change is involved, in that case correction is required for axial force effects, but here we are not we are writing for uniformly distributed case. So you do not have correction for axial force effect and torsional axial force and torsional moment, but we need to apply correction, fixed end solution correction for shears and moments. So moment My is given by this. The second part of this equation is fixed end solution correction coming from the case of coming from the case for uniformly distributed load. Moment mz is given by this. So, what we need to do is, given any problem, we need to assemble element equations in the local coordinate system and use transformation method and get the element equations in the global coordinate system, and based on the nodal connectivity assemble the global equation system, apply the displacement boundary condition, solve for the nodal values. Once we get the nodal values, we need to again find the corresponding displacements and rotations in the local coordinate system before we calculate axial forces, shear moments and torsional moment. So, this is the procedure. Now, let us take a numerical example. Analyze the frame shown in figure. Figure will be shown in the next slide. All members have same I shaped cross section and the flange dimensions, web dimensions and depth are given both in FPS units and SI units, and beam carries uniformly distributed load which is shown in the figure, and material properties are also given. So, here since the problem is given both in FPS units and SI units, we can work in any of the units, but here the workout is shown for FPS units case, because FPS units are round numbers here. So, this is the frame we need to analyze, 3-dimensional space frame, and if you see here all the dimensions are given, length of these members are given, and also global coordinate system is indicated in the figure, and also for each of the members local coordinate system is indicated, and also nodes are numbered. And please note that in this 3D space frame problem, for each element the equation size is going to be 12 by 12, and here we have 3 members. So, at each node you have total 6 degrees of freedom. So, total 4 nodes are there. So, 4 times 6, 24 by 24 global equation system we are going to get, in case we are going to assemble entire global equation system. But we can, instead of assembling the entire global equation system, because since here nodes 1, 2, 3 are restrained, all the degrees of freedom are 0. So, anyway in the global equation system, which is going to be 24 by 24, we are going to eliminate rows and columns corresponding to the degrees of freedom of these nodes 1, 2, 3. So, we are going to eliminate in total 18 rows and columns. Finally, we are going to get 6 by 6 reduced equation system. So, instead of assembling the entire 24 by 24 global equation system and reducing, we can smartly assemble the reduced equation system directly by noting down the contribution from each of the elements 1, 2, 3 to the locations corresponding to the degrees of freedom of node 4, because node 4 is the one which is for which we need to calculate all the degrees of freedom, 3 translational degrees of freedom and 3 rotational degrees of freedom at node 4. So we'll try to just assemble the matrix, even the element matrices, such a way that we carefully make sure that we have only the contributions which goes into the global equation system to calculate the corresponding degrees of freedom of node 4. If you see this figure, in the figure for each of the elements, even the local coordinate system is given, and since global coordinate system is defined, we can easily find what are the coordinates of nodes 1, 2, 3, 4, and also since the local coordinate system is also shown for each of the members, we can easily find what is the angle between local y axis and global axis, global y axis, what is the angle between local y axis and global y axis for each of the members, because if you want to use rotation angle methods, rotation angle method for calculating the rotation matrix, sorry, orientation angle method to calculate the rotation matrix, you require this angle which is angle between local x axis, sorry, local y axis and global y axis measured in the counterclockwise direction. So if you see, for let us say element 1 is the one which is connecting nodes 1 and 4, and if you see for that element, the angle between local y axis and global y axis is you can check, it is 180 degrees or alpha, sorry 180 degrees or pi radians or 180 degrees. So using orientation angle method, we can easily find what is the rotation matrix once we know this angle between local y axis and global y axis for this particular element, and also once we know the coordinates of nodes 1 and 4. And similarly, orientation angle alpha for element 2, which is connecting nodes 2 and 4, it is you can easily check the angle between global y axis and local y axis, it is equal to 0. So using this information we can find, and once we know the coordinates of nodes 2 and 4, we can find what is the angle between, sorry, you can easily find what is this rotation matrix. Similarly for node 3, so for element 3 which is connecting nodes 3 and 4, the orientation angle is 1.5 times alpha, sorry 1.5 times pi, that is 3 pi by 2 radians or 270 degrees. So using this information we can easily write what is the rotation matrix, and from there we can get the transformation matrix from the for the local to global coordinate system. So now that is how you can use the rotation angle method, or we can use third node method. Here for illustration purpose for this particular problem, we will use third node method to calculate the rotation matrix. So now let us proceed with this information, and from the given dimensions and cross sectional properties, and also if you see each of these members, y axis is minor axis z axis is major axis. So, from the dimensions and cross section properties we can get these values that are given, and from this we can calculate what are the coefficients A1, A2, A3, A4 for each of the members. But in this particular problem all the members are identical. Since all elements are identical, local element stiffness matrix for all elements is same, which is going to be 12 by 12 . So, this matrix is obtained based on the orientation of the members such a way that y axis is minor axis and z axis is major axis, and for all elements this is going to be the local stiffness matrix because all the elements are identical. So, now element equations in global coordinates. So, we obtained element equation in local coordinate system. To get element equations in the global coordinate system we need to apply transformation method. For that as I mentioned we will be using third node method to get the rotation matrix. The local axis for each element are shown in the figure, and you can see here we need to identify third node for element 1, element 2 and element 3, and third node is not something, is not going to be a point, something which is outside the structure. It can be, but in this particular case let us make sure that third node is defined based on a point which is there already existing in the model. So, for element 1 which is connecting nodes 1 to 4, third node is going to be node 2. For element 2 which is connecting nodes 2 to 4, third node is going to be 1. For element 3 which is connecting nodes 3 to 4, third node is going to be 2. And please note that element 1 is oriented such a way that it is going from, it is along a vector going from nodes 1 to 4, and element 2 is oriented such a way that it is along a vector which is going from node 2 to node 4, and element 3 is oriented such a way that it is along vector going from node 3 to node 4. So, we just identified what are the points which are going to act as third node for each of these members. We can put this in a table. These local axis using third node method will be computed if element nodes are defined as follows. Since one node of each element is fixed, only matrices associated with degrees of freedom at 4 are given below. So, this is what I mentioned, since nodes 1, 2, 3 are fixed or restrained for all degrees of freedom, we will be assembling the contribution which goes into the global equation system, which corresponds to the degrees of freedom at node 4. So, now we need to assemble the element equations for each of these elements. For that we need to get the rotation matrix. So, we will start element 1, node 1 the coordinate values, node 2 coordinate values, and we identify what is node 3 for third node for element 1, that is node 2, the values of coordinates are given. So, using this we can calculate Lx, Mx, Nx, and cross product of vector which is joining nodes 1 and 2, first node and third node, and cross product of that a vector which is joining first node to third node with a vector which is joining first node to second node gives us local y axis, and the cross product is shown there in this slide. So, Ly is equal to 0, My is equal to -1, this is the vector in the local y axis, and when you normalize it we are going to get 0 I -1 j plus 0 k. So, Ly is going to be 0, My is going to be 1, Ny is going to be 0, and we require another quantity Ly which is going to be square root of x square, sorry xy square, yy square, zy square, where xy, yy, zy are defined based on the coordinates of nodes 1 and first node, coordinates of first node, second node and third node. So, Ly if we calculate it turns out to be this, and Ly, My, Ny values are given there. So, now we got the local y axis, cross product of local x axis and local y axis gives us local z axis. So, that is what is the cross product is shown here, and also we require a quantity called Lz which is xz square plus yz square plus zz square, that is also given, and Lz, Mz, Nz, the vector z which is -240 I plus 0 j plus 0 k. If you normalize with respect to the magnitude of this vector, we get unit vector along local z axis, and that the components of that which is going to be Lz which is going to be -1, Mz is going to be 0, Nz is going to be 0. So, we got Lx, Mx, Nx, Ly, My, Ny, Lz, Mz, Nz. So, we are ready to write the rotation matrix corresponding to element 1, and this rotation matrix, this same rotation matrix can also be obtained using orientation angle method, noting that the angle between local y axis and global y axis for this particular element is pi degrees. The same r can be obtained using orientation angle approach with alpha is equal to pi radians. With this r, transformation matrix T is constructed and element stiffness matrix in global coordinates can be obtained by this formula, k is equal to T transpose KLT where the contribution to the global equations, global element equations corresponding to the degrees of freedom at 4 node 4 are shown besides this matrix U4, V4, W4, theta x4, theta y4, theta z4. And please note that here in this particular problem, for element 1 which is along a vector going from nodes 1 to 4, the load which is uniformly distributed load, it is applied in xy plane. So, using the formula corresponding to the equivalent load vector for distributed load applied in xy plane, which is qy L over 2 qy L square over 12 qy L over 2 minus qy L square over 12 transpose of that is going to be the local load vector. This load vector in the local coordinate system can be converted into the load vector in the global coordinate system using transformation method to obtain equivalent load vector in the global coordinate system. So, RQ in the global coordinate system is given by this one. So, this is equivalent load vector for element 1 in the global coordinate system. Similarly, we need to assemble stiffness contribution to the global equation system from element 2 and element 3, and also for element 2 we have to assemble this equivalent load vector because distributed load is applied on element 2. So, we need to repeat calculations for element 2, noting what is the first node, what is second node, what is third node, for calculating the direction cosines using third node method. And also we can obtain, if we wish, we can even obtain this rotation matrix using orientation angle method by noting that orientation angle between local y axis, local y axis and global y axis is 0 for this particular element. This is going to be the rotation matrix, and contribution to the global stiffness matrix is from this element is this, and this is only a partial matrix because here we are noting only the contribution that goes into the global equation system corresponding to the degrees of freedom for node 4 and equivalent nodal load vector. And similarly, we need to get for element 3 first node, second node and third node, and using this we can easily calculate what is the rotation matrix. Same thing we can also calculate using orientation angle method. And the stiffness contribution to the global equation system is this one. So, summing up all the contributions, a global system of equations after imposing boundary conditions is a 6 by 6 matrix, involving degrees of freedom corresponding to node 4. These equations can be obtained by simply adding the 6 by 6 element matrix associated with node 4 or local node 2 of each of these elements. Thus, global equations is obtained by this, that is whatever stiffness contribution we got from element 1, element 2, element 3, if you sum up we get this stiffness matrix which is shown in this slide, and force vector is also obtained by summing up equivalent load vector from element 1 and 2, and solving the 6 by 6 equation system we get the nodal solutions of corresponding to node 4. The solution corresponding to node 4 u4, v4, w4, theta x4, theta y4, theta z4 are given there, and these are the values in the global coordinate system. Element end forces can easily be obtained by first determining local displacements and then using shape functions and their derivatives. So, whatever the values here that are given are in the global coordinate system. So, we need to calculate what are the corresponding values in the local coordinate system, and please note that we numbered elements such a, or we numbered nodes such a way that for element 1 goes from node 1 to node 4, element 2 goes from node 2 to node 4, element 3 goes from node 3 to node 4. So, the nodal values for each of these elements in the local coordinate system turns out to be the same nodal values at element ends using transformation matrix and the global displacements, we get nodal values at element ends. These are the nodal values in the global coordinate system for each of the elements 1, 2, 3, and once we get this global displacement vector, we can use transformation matrix and get the local displacement vector. The quantities for element 1, length, using transformation matrix we can get nodal displacements in the local coordinate system, and the displacements in the local coordinate system turns out to be this. And once we obtain the displacements in the local coordinate system, we can calculate axial forces, shear, moment and torsional moment at both ends. So, for element 1 axial force is obtained using this, all units are in FPS units, and shear we need to apply the fixed end correction corresponding to distributed load, and this is going to be function of S. So, substituting S is equal to 0, we get shear at node 1, and S is equal to, substituting S is equal to 1, we get shear at node local node 2 or node 4 in the global node numbering. And similarly, the other shear component Vz and it is constant, and moment My with fixed end solution correction. Simplification of that gives in terms of S is equal to 0 corresponds to node 1, S is equal to 1 corresponds to global node 4, My value at these nodes 1 and 4. Similarly, Mz component, simplification of that gives us Mz component in terms of S. So, by substituting S is equal to 0 and S is equal to 1, we get Mz values at nodes 1 and 4, and torsional moment Mx, and these are the axial forces, shear moment and torsional moment for element 1. Similar calculations can be repeated for element 2. Details are not given here, final values are given. This is the torsional moment mx, my, mz. Similarly, for element 3, axial force, shear components, moments, so once we obtain axial forces, shears, moments, we can draw free body diagram. The forces can be shown on element free body diagram like this, and we can check the equilibrium of each of these element for numerical accuracy, and also we need to make sure that all the elements put together are in equilibrium. So, that helps us to check the numerical accuracy, and it can be easily verified. Indeed, whatever values that are obtained here satisfies all the equilibrium conditions.